Hello and welcome to SimScale's webinar on thermal bridging and heat conduction. First of all, I would like to thank all the attendees for joining this presentation, and we'll take a look at the thermal bridging and heat conduction in detail today. My name is Ajit Kumar. I work as an application engineer here in SimScale for the past 2.5 years, and I have a background in computational engineering from Rover University, Bochum. And joining with me today is Dr. Nagman Khan, who is one of our enterprise account manager at SimScale. He is well experienced in simulation and has a PhD in building simulation and is a secretary of CIBSC Building Simulation Group in the United Kingdom. Also joining with us is our product owner, Richard Suler from SimScale. He is actually taking care of the product development for our FEA and also heat transfer applications. All right, for new people, let's see about SimScale, who we are and what we actually do. So SimScale is a web-based simulation tool founded in 2012 in Munich, Germany. We are based in Munich, Germany, but we have currently set in offices in New York and Boston in the North America region. And what we particularly do, as a simulation tool on cloud, we are one of the first tool which is totally integrated on cloud, and every simulation aspect is and can be actually done using a simple web browser and internet connection. We have around 150,000 users worldwide and also 300,000 simulation projects on the cloud. We do not in particular just CFD or FEA. We have a variety of analysis type that can be actually done using SimScale on the web-based browser tool. All right, and today's application is thermal bridging and heat conduction. I'll let my colleague Nagman to explain a little bit on the agenda here.
Ajit, thank you so much for the introduction and welcome to all the attendees. This is a fascinating topic on thermal bridging and heat conduction, which is today's application. So what we're going to do is my colleague Ajit will give you a background to begin with about what is thermal bridging and heat calculations and how they pertain to certain standards which are used to comply with various jurisdictions. We're going to try and understand why thermal bridging is important and what circumstances is it needed, and a quick look at the end on how to get started with simulation. If you're new to SimScale and you've never used SimScale before, it's very easy to create a community account and get started. And actually this project we can share as well, so you'll be able to get started with a template project. From my own experience working in industry, I know thermal bridging is so important when it comes to calculations, for example, energy calculations for buildings, new buildings, whether it's homes, residential or non-domestic buildings, such as commercial buildings. And it's a requirement. You have to do this to comply with various standards. For example, the passive house standard. A lot of you might be familiar with that. So let's jump in. I'm going to hand over to my colleague Ajit for the introductory presentation and then the live demonstration. And then at the end, let's take some questions. Please also post your questions using the questions pane in GoToWebinar. And as they come through, we'll take a look at them. And towards the end, we'll make sure we answer as many questions as possible. Thank you.
Thanks, Nagman, for the brief introduction on SimScale and thermal bridging. Let's jump into the main focus of the application for today, the thermal bridging itself. At the first few slides, we talk about what is thermal bridging, where it can happen, and then also take a look at how these things are regulated for building envelopes, how we can actually measure thermal bridging or identify them using simulations. And then we'll also take a look at how the SimScale platform looks like, how we can perform thermal bridging using SimScale. So let's get to it. All right, first of all, what is thermal bridging? Thermal bridging is a localized phenomena which is generally happening in building envelopes or structures where there is a difference in heat flow or thermal conductivity when compared to the adjacent components. For example, you can see on the right, we have a corner, there is a wall junction, and there are like 2 or 3 corners meeting at a certain point. And in this case, the heat flow from the external or the internal side might actually produce some sort of heat flow through the walls itself. And this will cause the thermal bridging to happen actually. On the left, you can see a simple case which is simplified, which is a wall with insulation layers, and we have like two different ambient conditions from the external or internal side, one being hot, one being cold, and hence there is a temperature difference, and this leads to thermal bridging in this particular wall section. All right, let's see where this thermal bridging phenomenon can actually happen. So if you consider a nominal house, and then you see there are certain aspects to the house, which includes the roof, doors, windows, and also corners, just like we saw on the previous slide. And thermal bridging can happen anywhere locally where there are like two different ambient conditions. With respect to the temperature, if there is like a high and low temperature, there is going to be definitely some effects on the thermal bridging happening. And in particular, you can actually consider the window frames or facades or glazing, where these thermal bridging effects are like significant, and depends upon the external temperature also. Usually during hot climate conditions, thermal bridging is a particular player for all these damages to the buildings or even the window frames or glazing. All right, let's look at them in detail. So as I mentioned, like it can happen on the roof. If you have a window on the roof, it can happen to the frames, or even the roof itself can act as a thermal bridging subjection. So also on the corners, you can see if there are like 2 or 3 floors or stages of your building, and there are different temperature conditions from each of the stages, then that might be a position where thermal bridging can actually happen. And having take a look at like where thermal bridging happen, we need to actually consider why we should actually care for thermal bridging and how it actually affects in real time. So this can be actually put into two effects, the primary and the secondary. And the primary effects are more general. You can actually see them in a day-to-day life, like mold development in your corners or your roof or walls, and also condensation of your window glazing or your window frame itself. So this might happen during high humidity range and also high temperature difference between the ambient and the internal temperature conditions. And these primary effects will in turn cause major secondary effects like the damage to the material of your building structure or the window frames itself, or it will tertiarily create unnecessarily heat loss between the internal building envelope to the external or ambient temperature. And this can also alter your temperature conditions. And this might look like simple effects that is happening in your day-to-day life, but according to a study, the heat loss due to thermal bridging may actually account for 11 to 29% of your energy demand for heating. So in case if you have a HVAC system and it underperforms, or if there are thermal bridging issues in your building envelope, this energy demand might actually increase up to 29%. That is something serious and needs to be taken care when you even design a building or in the design phase of a building or architectural firm itself. And on the right, let's see what we can actually save when you actually integrate or plan properly for thermal bridging in the design phase itself. Because once when the building is erected and once when all these materials are already set, it's pretty much hard to actually replace them, or it might cost you a lot in case if you're affected by mold or any other tertiary effects that we have already seen. So in order to avoid that, we need to actually integrate this into a design workflow before the production level architecture. So in the design phase, if we want to include thermal bridging, we need certain tools to actually identify where thermal bridging can happen and also how we can avoid or how we can design things which can prevent thermal bridging. And first of all, let's look at a fact. So according to the same study, if you actually plan for the thermal bridging and make sure we don't make the materials or the building envelope prone to thermal bridging, we can all actually save up to 8% of the energy demand annually. And this study was done in a hot, humid climate, but this also affects for the other region of the world where the temperature differences are pretty much higher. the internal and the external side. All right. Just imagine that we actually integrated the thermal bridge planning in our design system, and the next step is to actually identify how the thermal bridging can be actually measured, or how we can identify whether the thermal bridging will happen or not in a building envelope. So to do this, there are certain standards for the engineering building developments, or there are regulatories based on which there are certain conditions to be satisfied to avoid thermal bridging or to avoid even the growth of mold or material damages. For example, we have this DIN 4108. This is a particular standard which deals with the thermal bridging effects, and this actually talks about a particular scenario where the external temperature is considered to be -5 degrees Celsius and the internal temperature is considered to be 20 degrees Celsius on an average. And the DIN standard states that if the temperature falls below 12.6 degrees Celsius on the internal side, there is a high chance of mold growth and also material damages to the wall structure itself. So it's important to actually maintain these kind of temperature differences and keep the temperature above 12.6 degrees Celsius for this case, to make sure there is no thermal bridging happening in your building envelope. And to make it a general factor, they have actually come up with a certain factor called the factor RSI, which actually means the internal minimum temperature of your surface in your building envelope. So this factor has to be kept above 0.7 to make sure thermal bridging is avoided and the building design is not subjected to thermal bridging. And on the other hand, so since we want to integrate this in our design phase itself, so we want our design engineers to actually use some sort of virtual tool or simulations to make sure the thermal bridging is not happening. And we do have certain software acceptance criteria based on ISO 10211. And this software acceptance criteria actually states the tool that we use for thermal bridging should not actually have much discrepancy with the analytical results. For example, if we calculate something out of a software based on the temperatures should not be more than 0.1 degree Celsius discrepancy or tolerances than the analytical solution. So this makes sure that the software you use is apt for the thermal bridging application and is actually comes under the acceptance criteria to be used for a larger or whole building envelope itself. So we'll take a look at how SimScale performs on this standards or the acceptance criteria, and also we'll jump onto SimScale platform to show you how you can easily set up these kind of simulations. But before moving into the next step, if there are any questions, please feel free to use the chat option. Write your questions there. By the end of this session, we'll discuss and also answer some of your questions. All right. We spoke about the simulation and the role of simulation in actually helping the thermal bridging effects and also how to prevent them. So we can put this into two main categories. So if you take a simulation, you can actually analyze the existing structures to make sure if you're under the compliance or if you're actually prone to thermal bridging, and then you can take measures based on that. And also in your design phase itself, if you know that some wall structures or building structures are prone to thermal bridging, you can actually iterate on the material properties and also add definite insulation layers in the simulation and then check whether the compliance standard is met or not. This will save a lot of time in the design phase and also make sure the final product or the building is not prone to thermal bridging. Yeah, and as you can see, the results from the simulation is highly based on the temperature itself. So what we are going to see in the simulation result is mostly the temperature results and also the heat flow or the heat flux. So we are going to compare that with the analytical solution and then see whether the software performs, and also this can be used for real-time applications to compare that with the DIN standards to make sure we are under the compliance. All right. As we spoke about the acceptance criteria for the software tool to be used for thermal bridging, so we actually ran few cases with SimScale and we actually compared that with analytical results. So on the left side, you can see a simple square column. We simulated the temperature distribution, extracted the temperature values at certain points, and compared that with analytical. And we found out that it's very much less than a percentage of difference between the analytical and the simulation results. And this goes the same for the other models with the corners or the wall joints, and also some sort of cantilever beam where we measure the heat flow and also the temperature distribution. All right. So let's actually jump into SimScale and see one of the cases here. We're going to talk about the cantilever case, and I'll also explain a little bit about how we can set up these kind of simulations easily with SimScale and extract the results. All right. This is SimScale platform, and we are into the post-processing scene of SimScale. So here is where you can actually take a look at the results, compare your results, and also analyze what kind of temperature is present in your simulated model. And for people who are new to SimScale, SimScale is a web-based simulation tool. You can access it anywhere in the world if you have just a browser and an internet connection. And this can be accessed by getting into the browser, typing in simscale.com and signing up. Once when you signed up, you can actually start simulating different kind of analysis types from that point on. All right, let's get into this particular case. So this is actually a cantilever case which is attached to a wall, and we want to see what is the heat flow through this cantilever and also to the external condition. So here you can see the temperature ranges from 0 to 1. This is based on a validation case, but this temperature ranges can be scaled or even simulated with different real-time conditions. All right, so the temperature gradient is from 0 to 1, and you want to see what is the heat flux through this system. So in the post-processor, you have the possibility to actually check the gradient visually, just like what we are seeing on the screen. Or if you want to check the temperature at a particular point, you can use the option inspect point and check wherever you want to actually measure the temperature. And in case if you want to actually derive the heat flux out of the system, then you can also change the variable to heat flux. For example, I'll go for magnitude, and you can do the inspect point option, or you can actually get a surface-based value if you click on the bulk calculator. So the bulk calculator actually gives you the exact value in your selected cutting plane or the plane that you want to analyze. It gives you the minimum, average, and the maximum value of the field variable that you've selected. So in our case, the heat flux is given from the minimum, average, and the maximum values. So based on these values, you can also compare it with the DIM standards to check whether your model or your building is according to the compliance or not. All right. Now that we have the results on screen, let's take a look at the simulation setup itself and how we can set these things up. So generally, starting with a simulation tool, you would need the CAD model. So it's similar to what we have in SimScale. So you can import your CAD model. We do support a lot of formats like STEP, STL, or even native formats like Parasolid, SolidWorks, Autodesk Inventor formats, and CATIA formats. So you can simply drag and drop your geometry here, and once when it is imported, you can take a look at the viewer. All right, when the geometry is here, it's pretty much a straightforward way to actually set up the simulation. You can create a simulation from this point, and SimScale actually supports a lot of analysis type, which can be based on the fluid flow simulations and also structural simulations. So here for this particular case, we need the structural analysis because we are going to measure the conductivity and the heat gradient in the solids. So we go for structural, and then we select the heat transfer simulation type. All right, when the simulation tree is generated on the left side of your screen, it's going to be simple. So you can see some red circles which needs to be addressed before starting the simulation, and these are simply 3 to 4 steps in maximum. So you have selected the geometry, you have selected the analysis type. Now you need to set the material that you want to simulate. For example, we'll go with concrete for the wall and a steel structure for the cantilever beam. All right. Once when the material properties are done, you just need to focus on the physics of the simulation. In our case, we need to actually set the temperature difference between the internal and external walls. So for example, we'll just go with the fixed temperature value. We give the external temperature as 0. We select the faces. And we do the same for the internal temperature. For example, you can give 1 degree Celsius or even 20 degrees Celsius if in case in reality you want to simulate a difference between 0 and 20 degrees Celsius. So just go with 1. And once when this is done, you can simply go ahead and start the simulation at this point. So the run might take like few minutes to compute, and you can see the estimation here when you start the run. So you can simply press start. And since we are totally cloud-based, once when you start the run, this is going to run on our cloud, and you can simply close your browser or even shut down your laptop and come back after some time and to actually check the results. So there's no need to actually hold the computer or the hardware system for your simulation to run. And also on top of that, you can also generate or start multiple runs at the same time. So for example, we just go back to the boundary condition. We want to analyze a 2 degree difference. So we just change this condition and start another run, which is going to run in parallel. So you can start as many runs in parallel. This is going to end up with the same time. And at the end of like few minutes, you can compare the results of all the simulations from here. All right, this is the exact workflow that you can use for these kind of analysis for thermal bridging. And once when the simulation is done, you would see a green check mark, which will be similar to what we have in a simulation setup we have already run. So you can see a green check mark here. And if you press that, you can directly go to the post-process results. This will take you to the post-processing scene where we were actually analyzing the results. All right, so this is a general workflow for these kind of simulations, but we also actually did a few other cases. For example, we did a case with the corners or the wall joint, and you can see the simulation setup is almost similar, but we have like a little more material properties for this case. So we have set like material for interior wall, isolation, insulation, and horizontal and floor structures. So you have like a additional condition to the settings, but the settings look similar for these kind of analysis. And once when the simulation is done, you can again go to the post-processing scene and start analyzing the temperature and the heat flux properties. All right, I'll jump back to the case we have explained. So at this point of time, thanks for listening, and also we are open for some of the questions to be answered now.
Ajit, thank you so much for that presentation and live demonstration. Great work. We have some questions coming through, Ajit. Should we take a few questions from the attendees?
Yeah, sure. Thanks, everyone.
Fantastic. If you're online, please feel free to send more questions. We're here for a few more minutes, and we'll be happy to answer any further questions. You can type them in the questions panel in GoToWebinar. So the first question is, can you take into account radiative heat losses from the building facade surface to the outside?
Yeah, that's actually a good question. So right now with the simulation, yes, you can actually take into consideration the radiative effects. This should be done by using a similar set of boundary conditions that you're going to use. So we can import some sort of formula that mimics the radiation effects, but we don't currently have the explicit feature to set radiation properties on the materials or the surfaces. So this has to be actually done with a formula-based boundary condition input.
Okay, so yeah, it's definitely possible with Okay, we have some questions here from attendees, Ryan and Stefan. Let's take a look. It's talking about the German standard DIN 4108 supplement 2. Are the templates integrated for that? And a related question, is there a calculation routine for separate calculation of radiation and convection in cavities? Any kind of insight into that? If there's any question we can't answer, we'll follow up with the attendees. So don't worry, and we'll also make the recording of this webinar available to everyone as well. So you'll have access to this recording. So Ajit, the first question was on German standard DIN 4108, and the second question is for separate calculation of radiation and convection in cavities. And our colleague Ricard is also on the line to answer any questions.
Yeah, I can start with the first question on the DIN standard. So there's no particular template for the result comparison, but you have all the possibilities to actually check the temperature and also heat flux. So you can calculate the U values and then compare directly with the results that you have on the post processor. So that is something possible within the post processor of SimScale.
Okay.
I hope that answers the question. Yeah.
Yep. And Ricard, you wanted to add some detail to the second part of the question.
Yes. Yeah, so taking into account cavities, so I think there are many methods how this can be taken into account. Traditionally, for FEA-based softwares, usually what you use is you use a simplification of the cavities based on rectangular patterns, and then you take a fake material based on the size of these cavities. That's one option that you can also do on SimScale. What we don't have is an automatic way to define something as a cavity and then automatically compute this surrogate material properties from that. You will need to do that manually. Alternatively, you can really physically model the air in the cavity, but for this you would need to refer to a slightly different analysis type, which would be the conjugate heat transfer analysis. That's also included on SimScale. It's computationally a little bit more expensive, but with that you have the ability to really model the air inside the cavity and then get also the results for these more complex cases. If there is interest, I think it would be also an interesting topic for another webinar to talk about these cases where we have air cavities inside and how we can deal with them.
Great, thank you, Ricard. Ricard, while you're on the line, there's a question about from Mr. Young about setting internal and external boundary conditions as per BR497 as opposed to the DIN method. Any comment on that, or is this something we can get back to Ryan on?
Yeah, I'm actually not familiar with every standard that's out there, but I can take a look and then follow up privately via email.
Sure. Okay.
Sure.
So
yeah.
No worries. Thank you. So Ryan, we'll get back to you on that. Great question. Thank you. We have another question from Dimitar. So it's, can we check complicated window sections? So windows which have multiple layers like glass panes, aluminium profiles, spaces, air cavities, things like that.
Yeah, I think that goes along the same lines as we just talked about, right? When you have air cavities, typically it's done using a simplified 2D approach. And then you have, again, these two options, either use the surrogate approach with some modeled air inside, but still modeling only conductivity, or you go the more complex analysis type, but higher fidelity model using our CHT approach. I think, as it already sounds, there's a lot of interest also in going after these more complex models. That would be, I guess, something we will have a look at in the next webinar.
Definitely, it's very topical. So Dimitar, to answer your question, yes, you can, and you can see on screen we have various types of analysis, right, depending on how complex you want the calculation to be. So our CHT, which Ricard mentioned, which is conjugate heat transfer, where you can use this type of analysis. And again, if this is of interest, we can create maybe a short Loom video or recording or something for attendees. Okay, we have a few other questions coming in. So how So Ajit, you were showing the simulation you did earlier. How long does a calculation like that take, and how many core hours would it consume?
Sure, Nagman. So the calculation which we actually discussed here, it's pretty much on the simple side, and the run actually takes around 3 minutes. It's gonna cost you around 0.5 koras. This is nothing to worry about. I mean, the run itself will take 3 minutes, and depending upon the complexity, it might actually go around 15 minutes at the maximum.
Okay, and core hours are cheap. They're just a few cents, something like that. Am I right, Ajit?
Yeah, that's correct. I mean, it's the amount of computational units that we use for the simulation time itself, and 0.5 koras in the standards is like really very few koras.
Okay, great. And we have another question. For someone who's new to SimScale, how easy is it to get started doing simulation like this? If someone's technical, an engineer or similar, but has never used SimScale, how easy would you say it is to get started? Follow some tutorials and be able to produce this level of simulation.
Yeah, that's a good question. I mean, it is in line with our vision of SimScale itself. So we want to actually democratize simulation to even people who don't have like extensive knowledge on any simulation tools or software analysis. So this can be easily done. As you can already see, the setup looks pretty much simple. You import the geometry and then set the conditions and start simulation. But in case if you're really novice to this kind of analysis type, we can also provide you with templates. So the run which we made actually can be shared with your account, and then you can easily check this or keep this as a reference for your future simulation. So it's going to be really easy. I can actually show you how to duplicate the entire simulation. So on screen, if we have a simulation that works, you can simply duplicate this one. You'll get an exact copy of it, and then you can start changing the geometry or even the boundary condition from that point using this as a template. So I would rather say like the workflow is pretty much made simple for design engineers to actually get access to the tool.
Great. And you mentioned geometry. Another question, like the last question, is about different CAD models and different types of CAD geometry you can import. Maybe you can just mention the different types and how easy that is and the kind of workflow to import geometry.
Sure, Nagman, thanks. Talking about the geometries, I mean, we do have like an extensive library of supported geometries. For example, you can import the native formats from SolidWorks, Autodesk Inventor, Rhino, CATIA, Revit, and also Creo. And also, in case if you have a complex geometry, you have in a certain format, like normal format like STEP, STL, or even the other IGES models, then you can simply drag and drop your geometries. So we do support like a wide range of geometries, and this shouldn't be any sort of issue for people who are not aware of the tool itself.
Fantastic, thank you. Please, if there's any other questions, I think that was the last questions. We'll stay on the line a few more minutes. Otherwise, I think we can end it there. If you need to go, feel free to go. If you have other questions, please post them. Just as a follow-up, just a reminder, so we will send in a few days' time a copy of this video with instructions on how to get in touch with us. If you want to go, if you want to access SimScale, or if you have a project where you think this might be useful, you want to discuss it with us, please get in touch. We can set up a demo for you and your team, show you how to get started, and perhaps answer any questions. Ajit, Ricard, any final comments from you?
Yeah, I would just like to add up a little bit on how to contact us. Maybe it's a good time to show them how they can easily contact us. So for the attendees, if you have a SimScale account, you can go to simscale.com, create an account, and if you're stuck at any point or if you have any questions, you can also reach out to us via the online chat. So we do actually respond within a couple of minutes, and then we can answer your questions or take the conversation from there. And obviously, you have the other channel via email, so you can send us an email and we can take it over from there. Yeah.
Great. Thank you again, everyone, for joining. Appreciate your time and attendance, and we'll be in touch with a follow-up of the recording and instructions on how to get started with SimScale. Thank you and bye.
Thanks, everyone. Bye-bye.